What we have here is a normal E-core transformer. All right, you have a center coil that you pulse into. It stimulates a magnetic field that goes around and stimulates electron flow into your pickup coils or into your pulsar coils. All right, this is where you tap off. You can either jump up your voltage or amperage. All right, so normal E-core, you can look it up. All right, what Thane Hines did is he came out with a secondary pathway. All right, so as normal cores, you pulse into this, it stimulates this. When this field collapses, it causes a greater impedance on your main coil, and that's what makes it consume electricity. Okay, so when you give it a secondary pathway, just like water, it always takes a path of least resistance, which actually decreases the impedance on these coils, decreases the impedance on this coil, and it makes it a lot more efficient. All right. So what I did was attach another set of Bi-Toroid to your secondary pathway. Okay, so all it is another Bi-Toroid that's attached on the secondary pathway. Now it's fractalized. All right, so as you pulse into your main core, the red one, and it stimulates electron flow in the secondary coils, and then that flow takes the secondary pathway. All right, it stimulates electron flow into your next main coil, which is just greatly increases the amount of electricity that you get out for what you're putting in. Okay, you can refer to Thane Hines on this. Now let's talk about materials. If it was built just normally using normal materials like they're made out of now, they're still not that efficient. But if you wrap your coils with microfine layers of graphene, and then you can look up the properties of graphene and see how efficient that graphene is at stimulating an electron flow. Okay, it's virtually a room temperature superconductor. Now let's talk about the material itself that's used in the basic framework. All right, so the E-core itself. Okay, you can use a room temperature superconducting conduit, which is not going to be easy to make, but essentially it's doped hydrogen. All right, you can encase each core in hydrogen, because the way hydrogen and graphene bond, the bonding angles make it a room temperature superconducting material. You can do the same thing for the cores. All right, now you get out a lot more than what you're putting in. And each core you can tap. Okay, so instead of pulsing into this one and only being able to tap that one, you know, this one or that one, so you jump up the voltage on this one and the amperage on that one, now you can control 6 more and tap off them. All right, so if you have a pulsing unit over here that's set up to a set of supercapacitors, then you can tap, say, this one or this one to recharge your supercapacitors that supply your pulsing unit that supplies your main coil. All right, so once you start it, it runs itself, and you have all these others that you can use to charge other supercapacitors. And now you have a unit that gives you more, way more, than what it cost you to put in. So you start it, it runs itself, it's solid state. It will last until a component breaks, a transistor or a resistor or a supercapacitor. All right, very simple.